Think about a force that can tell us the age of dinosaurs, light up our cities, and even cure cancer. Now, what if I told you that same force demands our absolute respect because it can also be incredibly dangerous? It's totally invisible, but it has shaped our world in some of the most profound ways imaginable. Today, we're diving into the power and the paradox of radioactivity.
All right, so here's our roadmap. We'll start with how it was discovered, completely by accident. Then we're going to journey deep inside the atom to see what makes it tick. After that, we'll meet the three main types of radiation, see all the amazing ways we've put this force to work, and finally, we'll get real about the dangers that come with wielding all that power.
You know, so many great stories in science don't start with a brilliant plan, but with a bit of sheer luck. In the discovery of radioactivity, it's the perfect example of how a simple accident can totally rewrite the rules of what we thought we knew.
So picture this, it's 1896. A scientist named Antoine Becquerel notices that a chunk of uranium is giving off these mysterious, invisible rays all by itself. This complete accident sparks the work of the incredible Pierre and Marie Curie, who just dive in and find even more elements doing the exact same thing. And all their work paved the way for Ernest Rutherford, who in 1911 finally gave us the modern picture of the atom, which was the key to understanding where these powerful rays were even coming from in the first place.
Okay, so to really get a grip on radioactivity, we have to zoom in. I mean, way, way in. We're going right into the heart of the atom itself, to the nucleus, because that's the engine room. That's where this whole phenomenon gets started. So what is it, really? Well, simply put, radioactivity is what happens when an atom's core is just unstable. It's like it's overstuffed and can't hold itself together anymore. So it spontaneously breaks apart or decays, and that process unleashes a big burst of energy that we call radiation.
This whole process is kind of like atomic alchemy, really. You start with this unstable element, which we call a parent isotope. As it decays, it shoots out energy and particles, and in the process, it literally transforms into a brand new, much more stable element, the daughter isotope. I mean, we are watching matter itself change from one thing into another.
Now here's a cool twist. While the decay of any single atom is totally random, when you get a bunch of them together, the process becomes incredibly predictable. And we measure this with something called a half-life. It's just what it sounds like, the amount of time it takes for half of the radioactive atoms in a sample to decay. This can be anything from a fraction of a second to billions of years, and it gives us a perfect atomic clock.
So, when an atom decays, it sends out this radiation. But here's the thing, not all radiation is the same. There are actually three main types. Think of them as three different messengers shooting out from the nucleus, and each one has its own unique identity and its own special power.
So let's meet the crew. We've got alpha particles, beta particles, and gamma rays. These are the three main ways an unstable atom sheds its extra energy and mass on its journey to finally becoming stable.
All right, let's break them down. First up, you have alpha particles. Think of these as the big, heavy bruisers of the group. They're basically a helium nucleus, so they're heavy and have a positive charge. Then you have beta particles. These are like speedy little bullets. They're just fast-moving electrons, so they're light and have a negative charge. And finally, you have gamma. Gamma is pure energy. It's got no mass, no charge, and it moves at the speed of light. It's a ghost.
And all those differences lead to one really important practical outcome: how easy they are to stop. That big, heavy alpha particle is easily blocked. You can stop it with a single sheet of paper. The speedy little beta particle will zip right through paper, but a thin sheet of aluminum foil will stop it. But that gamma ray, it's a powerhouse. It will blast right through both of those, and you'll need a thick slab of lead or concrete to even slow it down. Now, understanding all this stuff isn't just for a science test. It's actually allowed us to take this fundamental force of nature and turn it into one of the most powerful and versatile tools humanity has ever had.
Seriously, the applications are just mind-blowing. We use it in medicine for everything from X-rays to targeted cancer treatments. It's the nuclear and nuclear power that lights up our homes. We use it to sterilize food, to make new scientific discoveries, and even to power robotic missions to other planets. It's woven into the very fabric of our modern world.
Let's just take one amazing example: carbon dating. Remember that super predictable half-life we talked about? Well, scientists use it to figure out how old things are. They can dig up a fossil, clean it up, and use a special machine to literally count how many radioactive carbon-14 atoms are left. And based on that count, they can calculate with incredible accuracy how long ago that thing died. It's like a time machine for history.
Of course, there's another side to this story. For all of its incredible benefits, radioactivity comes with some very serious risks. The exact same energy that can be focused to destroy a tumor can also cause a ton of harm if it's not handled with extreme caution. It's a true double-edged sword.
So how does it actually hurt us? Well, you can think of high-energy radiation as a stream of microscopic bullets. They tear through our bodies, shredding our cells and our DNA. That kind of damage can cause immediate things like burns, it can mess up our body chemistry, and it can lead to devastating long-term problems like cancer.
This chart really puts it all into perspective. Down at the bottom in the green, you've got normal background radiation that we're all exposed to every day. No big deal. But as the exposure level climbs, the risks escalate, and they escalate fast. You go from a slightly increased risk of cancer to full-blown radiation sickness, and at the highest levels, it's just plain fatal.
So what's the big takeaway here? It's that radioactivity itself isn't good or evil. It's just a fundamental force of the universe, like gravity. It represents this incredible duality. On one hand, it's a source of immense power that can drive progress, but on the other, it's a source of profound risk that we have to manage with a lot of wisdom and a lot of caution.
When you strip everything else away, radioactivity is simply nature's engine of change. It's constantly transforming the world around us. So the real question isn't about the atom, it's about us. We're facing huge new challenges in energy and medicine. So how will we choose to use this powerful, invisible force? That choice is going to shape our future.